Hello again. So yeah, I'm recording this video to show another approach for the time traveling data structure problem and explain some things about the binary search implementation. So yeah, before we start to coding, let's just understand again the problem. And this is the problem. Again, not going to read it, but basically you need a data structure where for each key we store multiple values and each value is linked to a specific timestamp. So later someone could ask what was the value at a specific timestamp, and we need to return the latest value that was at or before that timestamp. So can be at that timestamp or before. So it's not just the specific timestamp. So yeah. Okay, so let's start to implement it. Mm, I'm gonna use Python to implement this. So last time traveling. Yeah. Again, we have to implement our basically structure here, our basically data structure, the data structure that will store the list of values for timestamps. So we can use just a dictionary here. So start. Okay, basically we have to implement two main operations, the put operation and the get operation. So the put operation is quite simple, right? We just need to add the key and then add our value. So put key and value. So this is the signature for the method. First, we have to check the key already exists in our store. So if the not in self the store, and if it's not exist, we just need to create it. So self store key. And then finally add your value, our value. So dot store the key and append to the list the timestamp value. So that's it. That just put some comments here to make the things more readable and clean. So dictionary where next is the timestamp value. Here we are checking if the key exists. So if key not seen, yeah, if the key not seen before, right? Set as empty list. So that's what we are doing here. So and then finally we just append our value. This is the the put operation, quite simple, right? So let's move forward and start to implement the dash operation. So get self key. Okay, some things about this. We could choose the easy implementation one, right? So the first idea is quite simple. We could, for every key, store all the timestamp values per in a list. And when someone calls get, we could scan this list from the beginning and keep track of the last valid timestamp. So we could just easily find it in our list of our all timestamps. So yeah, this actually could work. So the only problem is this is quite slow. So scanning this entire list could be taking a time of O of n. And this is not scalable because if the key has maybe 1 million integers, we may need 1 million comparisons to just answer one question. So uh, we'll have a better approach to solve this. And yeah, for smaller data sets, for small data sets, this actually could work, and we couldn't have any problem. But when this starts to increase, for sure the problem will come in. So yeah, so the idea here is not using the the iteration over the list, is actually use the binary search here because it's way best and takes a whole log complex for the operations. So yeah, let's implement the basically, and then we can discuss some things about it. So key not in but store. Here is simple, right? If our key doesn't exist in the store, we could simply return none, and it means that we can't retrieve any timestamp. So yeah. Now let's actually try to retrieve our array of timestamps. So in self.store. Sorry, oops. So okay, here is where the things to start to make sense and being interesting. So why binary search? So yeah, binary search is powerful here because we could check every element one by one, and when we check this element, we could divide the list in a half at each step. So for example, we could start in the middle of the array and then continuously dividing in a half until we find the value that we are searching for. So yeah, summarizing, we start the mirror, and if the timestamp is too small or if the timestamp is too big, we search. So if the timestamp is too small, we search the right half, the right part, and if it's too big, we just search for the left part that are smaller than our timestamp. So yeah, that's the decision that we need to make in every iteration. So okay, so here it's quite simple. From the formula, so we have to initialize our left and right. 8 minus 1. Let's initialize our response on top here. So and again, until this both parts, the left part and the right part, not being the same. So until the list still has two parts to be divided, we need to continuously find in the middle and then have by half our list to find the right value. So right, left. Yeah, that's it. So this is the middle, right? So this is the important part because, as I said, every decision that we have to make in this while cuts the list in two halves. So we always have to find the middle part, the mid part. So okay, if array dot zero. Here is our comparison, so we always try to compare the timestamp from the middle with the timestamp that we are passing for our method. So, yeah, so that, yeah, yeah. I think that's it. Let's let's put some. Let's try to test this because I'm not sure that I implemented correctly this thing. So, key. Oh, an important part that I forgot to mention is that we have to assume that every element in our list remains ordered. So we have to, for the binary search actually works, we need shorted list. So we can assume this because timestamps never decreases. So we also increase a timestamp, never decrease it. We can't be a time that regress. So this is why you can assume this for this problem. But if we couldn't assume this, we could just put a short here. So each time that we add a value to our list, we just need to return this list order. So, uh, but this doesn't necessary. Okay, so let me just check some things on the problem. Yeah, I think that's it. Sorry. Okay, let's print this. What is the problem here? Okay, let's see the comma here. Okay, now we can actually print this problem. So let's let's run here. So just let's save this thing. So dot line. Okay, so this have to be one car, right? Because we're not finding we're not passing n times temp bigger than 6. So this actually has to be one car. So let's run it. Okay, okay, good. Actually working. So Yeah, okay. I think that's it. Let's just put some more examples here. Make things maybe try to get 6 now to see what happened. So yeah, has to be needs to return jar. This is the right output here. So let's see. Okay, car and jar. Sounds good. Yeah, that's the thing here, right? So each decision we just cut the options in a half, and this make much faster to find our solution. So instead of using any steps or any any iterations for the to find the solution, uh, we just taking log n, so log n steps. So yeah, that's it. And again, for example, if you have 1 million timestamps, binary search would way better. And yeah, yeah, that's it. That's why this works so well. And okay, yeah, about the complex time here, it's full log of n, and the set operation doesn't have any complexity here, so it's constant, right? So we are doing to uh, nothing complicated here. So you're just in storing values. So the time complexity is okay. And yeah, you're just appending here, no problem. Yeah, here the time time complexity. Let's put some comments here. So instead of using we actually make it as so using if time binary search. Okay, so about the space complexity here, so for the put operation, the space complexity is O of n, so space complex is O. And why? Because we are storing in our list this timestamp, so this is actually increased in the same way that we are storing values, so we should increase this as O of n. And here again, also space complexity space complexity of of n, because we have to retrieve this array to make the binary search work. So uh, this array increases in the same velocity, in the same way that we are storing values input here. So that's it. Yeah, I think that's it. So thank you again for watching this approach and for watching this video, and have a good day. Bye bye.